out there in the silent, unending dark where distance is measured in lifetimes and the cold is absolute, something stirred. For uncounted millennia, it had drifted a ghost in the abyss, a frozen remnant from the dawn of our solar system. This realm, a vast spherical shell of trillions of icy bodies, is known to us as the Oort Cloud, the most distant frontier of our sun's domain. It is a cosmic nursery and a graveyard, a place of profound stillness where the sun is just the brightest star in a sea of indifferent lights. Imagine a kingdom so immense that light itself takes more than a year to cross it. Within this celestial sphere, countless primordial icebergs float in a delicate ballet bound by the faintest whisper of our star's gravity. They are the raw materials, the unused bricks and mortar left over from the construction of the planets 4.5 billion years ago. Each one is a time capsule, preserving the chemistry of that ancient nebula. For eons, this particular object followed its silent looping path, an enormous, aimless orbit at the edge of everything. Then, a subtle perturbation occurred, a cosmic nudge. Perhaps it was the gravitational pull of a passing star, a phantom presence in the interstellar night that disturbed its slumber. Or maybe it was a gentle resonance, a tidal force from the galaxy itself. The cause is lost to the immensity of time, but the effect was definitive. Its stable, leisurely existence was over. A new trajectory was set, a one-way fall spanning thousands of generations. It began the long pilgrimage inward toward the fire. On Earth, empires rose and fell. Languages were born and faded into memory. Humanity looked to the sky, charting the predictable dance of planets and stars. But this traveler remained unseen, an invisible spectre crossing the immense voids between the outer worlds. It passed the orbits of Neptune and Uranus, still a dark, inert object, its frozen heart, yet to be awakened by the distant sun's warmth. It moved through the realm of Saturn and Jupiter, its velocity increasing with every passing moment, a captive of the inexorable pull of the solar furnace ahead. Then, in the early years of the 21st century, our sentinels noticed. They are not human eyes, but robotic ones, tireless and ever vigilant. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of telescopes designed to scan the heavens for potential threats. On a routine night of automated surveillance, the system flagged a faint smudge of light, an unregistered mover against the static backdrop of distant galaxies. It was designated C-2025K1 Atlas, a formal name for an object of profound antiquity. The designation itself tells a story. The C indicates it is a non-periodic comet, a visitor on an open orbit that will not return for many thousands or perhaps even millions of years. A transient guest in our inner solar system. 2025K1 marks the time of its discovery and its sequence in the celestial ledger. But this sterile nomenclature belied the spectacle that was to come. Astronomers calculated its path, a trajectory of terrifying proximity to our star. It was classified as a Sungrazer, a member of an exclusive club of cosmic daredevils. The history of sun-grazing comets is a dramatic and often tragic one. We have seen them before, these icy sojourners that choose a path of solar immersion. Comet Ison, the great hope of 2013, was a spectacular example. It approached the Sun with great promise, expected to become a brilliant naked-eye object, but the combined forces of overwhelming gravity and unbearable heat were too much. Ison flew into the solar corona and never came out, disintegrating into a cloud of dust and gas, its journey ending in a fiery death. This is the expected fate for most who challenge the Sun so directly. So, as C-2025K1 Atlas plunged toward its perihelion, its closest approach to the Sun, the scientific community watched with bated breath and a sense of grim expectation. This was not merely a flyby, it was an ordeal, a trial by fire. Imagine a snowball trillions of tons of ice and rock hurtling through space at hundreds of thousands of miles per hour. Now imagine that snowball flying just a few million miles from the sun's surface. It enters a realm where the temperature leaps to millions of degrees, a furnace of unimaginable ferocity. The sun's radiation, a relentless blast of photons and charged particles, begins to violently strip away the comet's outer layers. The ancient ices, frozen for billions of years, do not melt. They sublimate, turning directly from solid into gas. Water, carbon dioxide, methane and ammonia, locked away since time's dawn, erupt from the nucleus in massive explosive jets. This outgassing creates a glowing atmosphere around the nucleus, the coma. The solar wind then sweeps this material away, forming the iconic tails that can stretch for millions of miles across space. Simultaneously, the sun's gravity asserts its dominance. The tidal forces are immense, a cosmic tug-of-war that tries to rip the comet's fragile nucleus apart. Fissures can form and deepen, causing the entire structure to fracture and dissipate. This is the crucible. An object forged in the deepest cold of interstellar space is now subjected to the most extreme heat and stress our system can offer. It is the ultimate test of its structural integrity. Most do not pass. But C 2025K1 Atlas was different. It plunged into the inferno, disappearing into the blinding glare of our star. For days it was lost to our view, its fate unknown. Telescopes waited, pointing at the region of space where it was predicted to emerge. Was this another Ison? Another ephemeral visitor, consumed by the very star it came to greet? Then against all odds, it reappeared, a faint but distinct point of light moving out from the sun's corona. It had survived. The celestial wanderer had flown through the heart of the fire and emerged, scarred and battered, but fundamentally intact. It was a moment of profound triumph and deepening mystery. This primordial iceberg was tougher than expected, composed of more resilient stuff. Its survival alone made it an object of intense scientific interest. But as it moved away from the sun and into the darker skies, observers began to notice something else, something truly strange. Something that challenged our fundamental understanding of these cosmic visitors. It was the color. Comets, for the most part, adhere to a fairly predictable color palette. When we see them in photographs, particularly their glowing comas, they are often imbued with a striking ethereal green hue. This characteristic tint is not arbitrary. It is a direct result of their chemistry. The green glow is the spectral fingerprint of a specific molecule, diatomic carbon, or C2. Imagine two carbon atoms bonded together, a simple but crucial component of cometary ice. As the comet nears the sun, these molecules are released and float in the coma. The sun's ultraviolet radiation then bombards them with energy. This process is akin to charging a fluorescent light. The UV light excites the C2 molecules, kicking their electrons into a higher energy state. But this state is unstable. Almost immediately, the electrons fall back to their original level. As they do, they release the excess energy in the form of a photon, a particle of light. For diatomic carbon, this emission occurs at a very specific wavelength, one that our eyes perceive as a vibrant, ghostly green. A similar process happens with the cyanogen radical, a carbon-nitrogen pair, which adds a hint of blue and violet to the mix. This green and blue luminescence is the classic cometary signature. But C 2205K1 Atlas was not green. It was not blue. As it receded from the sun, its full glory becoming visible against the black telescopes revealed a startling and beautiful anomaly. The comet glowed with a warm, rich golden-red coloration. It was the color of embers, of a dying fire, of a celestial sunset. This was not just unusual, it was profoundly weird. It suggested that the chemical processes happening within this comet were fundamentally different from what we had come to expect. The question echoed through observatories worldwide. Why? The first and most straightforward hypothesis centered on dust. A comet is not just a ball of ice, it is a dirty snowball, as the astronomer Fred Whipple famously described it in the 1952. Embedded within the ices are vast quantities of dust and rock primordial grit from the solar system's formation. When the ices sublimate, this dust is released and forms its own tail separate from the ion tail made of glowing gas. This dust tail shines simply by reflecting sunlight. Perhaps the unique color of Atlas was an illusion of scattering. We see this phenomenon every day on Earth. Our sky is blue because nitrogen and oxygen molecules in the atmosphere are the right size to scatter the shorter, bluer wavelengths of sunlight more effectively. At sunrise and sunset, however, the light has to travel through more atmosphere. Most of the blue light is scattered away from our line of sight, leaving the longer, redder wavelengths to reach our eyes, creating a spectacular display. Could a similar process be happening with this comet? If the dust particles being shed by C 2025 K1 Atlas were of a specific uniform size larger than the dust of a typical comet, they might preferentially scatter red light toward our telescopes. The golden hue would not be from the comet times emitting times light, but from the way its dust cloud times reflects times it. The sundive could be the key to this mechanism. The intense heat may have vaporized all the smaller, finer dust particles, leaving behind only larger, more robust grains. These remaining grains would then create the reddish scattering effect, turning the entire coma into a colossal cosmic sunset. It's a plausible theory, an elegant explanation rooted in simple physics. But other astronomers suspected something more complex, something related to the intrinsic chemistry of this ancient object. This leads us to a second, more exotic possibility: sodium. We know that sodium exists in comets locked away within their mineral dust. Under normal circumstances, it is not a major contributor to their visible light. But C 2025 K1 Atlas had just endured no ordinary journey. It had skimmed the surface of our star. The incredible heat of its perihelion passage would have been sufficient to vaporize not just ices but also minerals and metals from its nucleus. Sodium, with its relatively low boiling point for a metal, would have been liberated in vast quantities. Once in gaseous form and surrounding the comet, these sodium atoms would behave much like the diatomic carbon we discussed earlier. They would be energized by sunlight and emit photons at a specific wavelength. And the characteristic color of glowing sodium gas is not green or blue. It is a brilliant, intense orange-yellow. Think of the color of a sodium vapor street lamp. That distinctive monochromatic amber glow is the spectral signature of excited sodium atoms. If this comet had released an unusually large amount of sodium during its sundive, it could have created a massive glowing sodium tail. This bright orange-yellow emission mixed with the reflected light from its dust could easily combine to create the observed golden-red hue. The comet wasn't just reflecting sunlight, it was glowing with its own metallic fire, a celestial lamp powered by its near-death experience. This theory had the advantage of directly linking the strange color to the comet's survival story. Yet a third, and perhaps the most tantalizing explanation emerged, one that connects this distant visitor to the very origins of life itself. This hypothesis looks beyond simple elements and dust grains to the realm of complex organic chemistry. The idea centers on a class of molecules known as tholins. The term tholin comes from the ancient Greek for muddy or hazy, coined by Carl Sagan and his colleague Bishun Khare to describe the complex gunk they created in laboratory experiments simulating the atmosphere of Saturn's moon Titan. Tholins are not a single molecule but a vast, sticky family of organic polymers. They are formed when simple organic compounds like methane, ethane, or ammonia are irradiated by ultraviolet light or bombarded with charged particles. The energy breaks the simple molecules apart, and their fragments recombine into larger, more complex, and often reddish-brown structures. We see the signature of tholins throughout the outer solar system. They are responsible for the reddish haze in Titan's atmosphere. They paint the surface of Pluto with its characteristic dark red patches. They are found on many asteroids and Kuiper belt objects. They are, in essence, the color of primordial organic chemistry. What if C 2025 K1 Atlas was not from the Oort Cloud's icy mainstream? What if it originated in a region of the primordial solar nebula that was exceptionally rich in the simple organic compounds that form tholins over billions of years in the deep freeze of the outer dark? The faint but persistent cosmic radiation could have slowly processed its surface, blanketing it in a thick crust of these complex reddish molecules. This would make the comet itself, the nucleus, intrinsically dark and red. As it approached the Sun, the sublimating ices would carry these tholin particles out into the coma and tail. Instead of a cloud of reflective dust, the coma would be suffused with tiny particles that absorb blue light and reflect red light. The entire spectacle would therefore appear golden red, not because of light scattering or atomic emissions, but because the very substance of the comet was this color. This explanation is thrilling because tholins are considered to be potential precursors to the building blocks of life. They are just a few chemical steps away from forming amino acids and nucleotides, the very foundation of proteins and DNA. This theory transforms the comet from a mere geological curiosity into a potential messenger from our own deep past. The panspermia hypothesis suggests that life on Earth may not have begun here, but was delivered from space by comets and asteroids. A more moderate version of this idea, and one that is widely accepted, is that these cosmic bombardments delivered the necessary raw materials, water and complex organic molecules, to a young, sterile Earth. This allowed life to get its start in the planet's primordial oceans. A comet glowing with the ruddy tint of tholins is a stunning visual reminder of this profound connection between the cosmos and our own biology. It suggests that C 2025 K1 Atlas could be a pristine example of the very type of object that may have seeded our world with the ingredients for life. Its long, lonely journey from the darkness was not just a gravitational accident, but a pilgrimage carrying the chemical memory of our system's birth, and perhaps the potential for life itself. The weird golden red color ceases to be just a mystery of physics. It becomes a philosophical beacon, a link in the chain of cosmic evolution. Of course, these theories are not mutually exclusive. The ultimate truth behind the comet's unique coloration is likely a combination of all these factors. It is a composite masterpiece painted by multiple physical processes. The survival of its sundive might have left it with larger red scattering dust grains. The intense heating certainly vaporized a significant amount of sodium, adding a warm amber glow to its spectral signature, and its primordial composition, rich in tholins, could have provided the foundational reddish pigment for the entire display. C 2025 K1 Atlas is not just a comet, it is a laboratory, a celestial experiment, demonstrating the complex interplay of chemistry, physics, and cosmic history. To truly appreciate the significance of this golden red wanderer, we must step back and view it through the lens of human history. For most of our existence, comets were not objects of scientific inquiry. They were omens, portents of doom, celestial swords hanging in the night sky. The word disaster itself has its roots in this fear, coming from the Greek for bad star. The Bayeux Tapestry, which chronicles the Norman conquest of England in 1066, famously depicts King Harold cowering as Halley's comet blazes overhead, a clear sign to the people of the time that their world was about to be upended. These hairy stars, as they were called, were unpredictable, ethereal, and seemed to violate the perfect clockwork order of the heavens. The first great shift in our understanding came in the 16th century with the Danish astronomer Tycho Brahe. By meticulously observing a bright comet in 1577 from different locations, he used the principle of parallax to prove that the comet was much farther away than the moon residing among the planets. This was a revolutionary act. It moved comets from the realm of atmospheric weather like clouds or lightning to the domain of astronomy. They were not earthly omens, but true citizens of the cosmos. A century later, Isaac Newton's laws of universal gravitation provided the mathematical framework to understand their motion. It was his friend Edmund Halley who painstakingly applied these new laws to the historical records of various cometary appearances. He noticed a striking similarity in the orbits of the comets of 153, 11607, and 1682. He made a bold and unprecedented prediction that these were not three separate comets, but a single object, and it would return again in the year 1758. Halley did not live to see his prediction come true, but when the comet appeared on Christmas night of that year right on schedule, it was a monumental victory for science and reason. Comets were no longer supernatural terrors, but predictable physical objects bound by the same laws that govern the fall of an apple. The 20th century brought us Fred Whipple's dirty snowball model, which finally explained the source of their brilliant comas and tails. And then came the space age, which allowed us to move beyond mere observation. In 1986, an international armada of spacecraft, including Europe's Giotto probe, intercepted Halley's comet, giving us our first ever close-up images of a cometary nucleus. It was not a smooth, icy sphere, but a dark, irregular, potato-shaped body, blacker than coal, with bright jets of gas erupting from its sunlit side. Missions like Stardust captured cometary dust and returned it to Earth for analysis, revealing a treasure trove of complex organic molecules. The Rosetta mission spent 2 years orbiting Comet 67P, escorting it on its journey around the Sun, and even landing a probe Philae on its surface. Each of these steps has built upon the last, transforming comets from portents of doom to books of history. They are the most pristine samples we have of the early solar system. While the planets have been geologically processed by heat, pressure, and erosion, the comets have remained in a state of deep freeze for billions of years. Studying their composition is like performing an archaeological dig on the very foundations of our cosmic home. And that is why a comet like C 2025K1 Atlas is so profoundly important. Its survival tells us something about the formation of the Oort Cloud. Perhaps there are two populations of comets out there: fragile, loosely packed snowballs like Ison, and denser, more robust bodies like Atlas, capable of weathering a solar passage. Its unique golden-red color provides a new set of chemical clues. It forces us to reconsider the distribution of materials like sodium and organic tholins in the primordial solar nebula. It suggests that the building blocks of our solar system were not as uniformly mixed as we might have thought. There were regional variations, pockets of unusual chemistry, and this comet is a messenger from one such long-lost province. As C 2025K1 Atlas continues its journey. It moves back out into the cold and the dark. Its spectacular golden-red display will fade as it recedes from the sun. The outgassing will cease, the coma will dissipate, and the tails will vanish. It will once again become a single inert point of light, and then a faint smudge, and then nothing. It will cross the orbits of the outer planets, its velocity slowly decreasing as it climbs back up the sun's immense gravitational well. For thousands of years it will travel outwards, returning to the silent abyss from which it came. Its journey is a powerful meditation on the nature of time. The last time this object graced the inner solar system, human beings were living in the Stone Age, huddled in caves. The next time it returns, will humanity be here to see it? Will our descendants, perhaps living on other worlds, turn their own advanced telescopes to the sky to greet its return? Or will it pass through an empty solar system, its silent, golden-red pilgrimage, observed by no one? We are granted this one brief intersection, this fleeting cosmic encounter. The comet is a reminder that the universe is not a static stage, but a dynamic, evolving story. It is a story of immense violence and delicate beauty, of cataclysmic explosions and the slow, patient accumulation of cosmic dust. It is a story written in the language of physics and chemistry, in the spectral signatures of distant stars and the strange hues of visiting comets. The golden-red glow of C. 2025 K1 Atlas, the survivor of the solar fire, is one small, beautiful, and profoundly mysterious verse in that epic. It is a message in a bottle thrown from the sea of primordial time, and we are the fortunate ones living on the shore who get to read it. Its weird color is not just an anomaly, it is a revelation, a new clue in our unending quest to understand where we came from and what the universe is truly made of. Its light, having traveled for eons, finally reaches us carrying a secret of fire, ice, and the deep organic heart of the cosmos.